Okay, so welcome back. And what we're gonna talk about today, from today and maybe the next 3 lectures is going to be the Conor method. So it's going to be chapter 6. Of the textbook called Conor method. And then the kind of mathematics that you will experience, you will see in this chapter is a bit different from the one that you have seen so far. So far, most of the things will involve either a little bit of combinatorics and a bit more on the probability theory. But then the kind of mathematics that you will see in the Conor method are really coming from the functional analysis. Okay, but that's more mathematical side. For practical side, actually the Conor method is really important. So let me just start with some motivation. So the Conors mathematically are very simple. If we have an input space X, so that's an input space. And Conor is nothing but a binary function on inputs that returns some real number. And so that's the Conor, and typically we require this K has to satisfy so-called symmetry. And the other requirement is so-called positive definiteness. And we're going to talk about what they are later. Symmetry is obvious. What that means is changing the order of 2 inputs shouldn't really matter. But what's more important at this stage is that what K tried to capture. And K tried to capture the similarity of 2 inputs. If 2 inputs are very, very similar, so then K will return a large value. 2 inputs are opposite, that it will return very low value. Negative value with large absolutes. Negative value whose absolute value is very large. Okay, so the K measures the similarity of two inputs, and then the symmetry and positive definiteness really ensures that K is chosen properly to capture this idea of similarity, and the exact meaning will become a bit clear. Now, why Conor is important in machine learning, and there are 2 reasons why there are multiple reasons, but I want to mention 2. The first reason is that many machine learning algorithms can be extended or modified to work with kernels. So sometimes what people call this as a kernelization or kernel trick. And then one consequence is that, I'm going to tell you a bit more about give an example of what's really going on. But one consequence is that if you do so, then even when we can increase the power of the algorithm dramatically. Okay, so even though original algorithm just compute a linear classifier, if you apply the kernel trick, then we can change the algorithm so that it can work with non-linear classifier. So the typical example is a support vector machine. We said support vector machine can be the dual version of support vector machine, can be understood as solving the spiraling optimization problem. which is it computes the supremum or maximum of alphas, use alpha, which are dual variables, where the optimization objective was supremum, I think it's, yeah, it's a supremum of alpha through m alpha I minus ij m alpha I alpha j yi yj xi inner product of xi and xj, subject to the condition that the alpha I is within this range, and the sum of alpha I yi should be equal to 0. That was the dual version of support vector machine for the general case. And then once we solve this optimization problem, then the linear classifier we're gonna obtain is of the form. So we compute functions, which is weights times x plus some bias b. But then if we have a solution of the one above, w optimal value will be computed, right? Optimal will be computed by optimal value of alpha I, so yi xi, and b star will compute it in certain way. So you're using certain alpha I, which is different from 0 and different from c. So that's what we learned before. But then we also learned that if we do so, we can actually write this f star in terms of inner product only. I star, yi, xi, and x plus b star. But it turns out, for support something like the algorithms for support vector machine, we can extend it. So we can change this algorithm, because this algorithm only depending on the kernels, I mean the inner products, when you solve the optimization problem. In other words, when you do the training, as well as when you use the trained outcome and to make a prediction for the new inputs, it also uses only the inner products. We can change this algorithm using the kernels, so that we, instead of computing the inner products, we compute the kernel value of xi and xj. Also for the classifier, which is computing this f star of x and then taking its sign and then classify plus and minus based on the sign. Once we solve the optimization problem with respect to modified optimization problem using the kernels, then we can also use the classifier, which uses a kernel. So for kernel, which say xi and x. And then by changing this, we can obtain a new algorithm, and we can also justify why using this new algorithm makes sense. In other words, many of the theoretical guarantees that we proved using about support vector machine can still carry over in this new regime. And as we will see later, this is not a coincidence. There are so there is something called representative theorem, which is say that many of the which doesn't directly tell us that many machine learning algorithm can be generalized using the kernel tree, but it indicates similar kind of kernel versions, or kernel generalized version can exist applied for many machine learning problems. Okay, so the first point about the kernel is that it allows us to generalize the existing machine learning algorithm, and in doing so, what we can obtain is that now the outcome that we obtain in this case is, the classifier that we obtain here is going to be a nonlinear classifier with respect to the parameter x. Although the entire SVM algorithm is derived and analyzed based on our understanding of the linear classifier, if you kernelize it, then the outcome we obtain from the kernelized extension of the algorithm will be a nonlinear classifier. So let me mention one more thing about what's really going on here. What's really going on here is that many of these kernel algorithms, the kernels, what it does is that, especially if it satisfies the symmetry and positive definiteness, what it does is that it computes the inner products. So it implicitly represents a feature space, okay, some feature space which I will call H. There's something called the reproducing kernel Hilbert space. So there's just some feature space without really defining it. And then there's a feature map, which take each input x, and return an element in the feature space. So this feature space H may be sometimes some Euclidean space with very high dimension, or sometimes, although this is not the exact notation, is an infinite dimensional Euclidean space. Okay, so there are some feature space, but which is implicitly defined by the kernels. And what kernel does is that it computes the inner products in this infinite dimension, well, in this implicitly defined feature space. And these two conditions that I talked about, the symmetry and positive definiteness, ensures that this is always happening. There are any kernels which satisfy symmetry and positive definiteness. There is an implicitly defined feature space. And then the kernel K is really represent input using the feature vector in the space and then computing the inner products. So that's what this kernel is doing. And if you view this, view it from this perspective, what's really going on in this generalization is that any algorithm that using the linear classifier in one way or another, like a support vector machine and so on, they can all be generalized. So by using the kernel trick, they get generalized to work with not input, but a new type of features encoded by this feature vector phi. So they kernelized version of the algorithms embed or convert all the inputs using this feature map phi. So using this feature map phi, it converts all the inputs to a feature vector in some implicitly defined space, and then run the original algorithm with respect to this implicitly defined feature space. Okay, but if you come back and view what's really going on from the original space of x and x prime, then it increased the power because using K means we are using very expressive features. Okay, so generalization of an algorithm is one aspect, one reason why we are interested in kernel method. The other is that, so that's more practical side. The other reason is it also comes with very nice mathematical theory. The kernels have nice mathematical theory. And so as a result, we can analyze many existing machine learning algorithms using this theory for the kernels. Algorithms. Intuitively, what happened is that, the kernels and then allows us to rephrase complicated machine learning algorithm as some form of algorithm that work on linear classifier. So you maybe try to find a linear classifier in a highly complicated feature space. But if for the linear classifier, we have a very powerful tool called linear algebra or functional analysis. And if you apply these tools, then we can analyze these complicated machine learning algorithms. So one example that happens recently is that analysis of infinite width neural network. So, showing anything formal about neural networks is really hard, but it turns out if you send width to the infinity, so the neural network with very large width, then these kind of objects, and this neural network converge to something, and then the analyzing such network can be done using so-called the kind of mathematical theory we're going to cover in this chapter. So in other words, the techniques from the Kernel method can be used to analyze the infinite width neural network. So if you are interested in for instance, we can prove in this idealized neural network, if you train on the mean squared loss, it always achieves zero errors. The gradient descent will always achieve zero error eventually. So that's one of the results you can show. And there are some other results you can prove about this, about the neural network, the initialization as well as training. So if you're interested in, we are not going to cover this, but if you're interested in about this, then you can see something called, if you Google NNGP, which represents neural network Gaussian process, or NTK, which is a neural tangent kernels in the Google, then you can get appropriate references on this topic. Okay. So that kind of is a motivations, and then the focus. We're gonna cover mathematical theory. So that's what we're gonna cover throughout in this chapter. But also we will talk a little bit about how kernels can be used to generalize the machine learning algorithms. Okay, let's go to the definition of the kernels. So what is kernel? So particularly we are interested in so-called positive definite symmetry kernels. So this is, we will use abbreviation quite often, which is PDS kernels. So this is the object that we're going to study. And then the question is, what are they? So here's the definition about the positive definite symmetry kernel. So a kernel, by the way, we just assume there is just an input space X, so space of the inputs. Typically, it's a subset of the Euclidean space, like Rn, but it can be anything. It doesn't really matter. And then a kernel is just a real valued binary function K on X. In other words, the kernel is nothing but function of the following type. You take two x's and then return the real number. So that's the definition of kernel. Then we say Conor K is positive definite and symmetric. So that says P, yes. If it satisfies the two properties, so that means that the first property is that for all real number, no natural number, and then for the C1 up to Cm, so m real numbers, and then x1 up to xm, m inputs. If you compute sum of Ci, Cj, so we sum over all ij from 1 to m, k, xi, xj has to be greater than or equal to 0. So that's the first property. And that is related to this positive definiteness. So this positive definiteness refers to this condition. And then the second property is a symmetric, which is quite obvious. Say that for xx prime, two inputs, computing x prime is same as computing prime. So that's related to the symmetry property. Symmetry is related to this second property. Then you might wonder, okay, why do we impose these two properties? And one answer is that if Conor K satisfies these two properties, it can be understood as essentially computing on inner products. Okay, but we don't really know at this stage which space it is using, but there is some space where inner product is well defined. It's maybe different from X, the input space. There are just some space, and we have a feature map that maps each input X to that big space, which allows us to compute the inner product. And that if Conor K satisfies these two properties, we can always understand K as a first embedding into some space, some larger space potentially, which allows us to compute the inner product and then computing the inner product. So notice if y1 and 2, intuitively it means because if K satisfies these two, then K behave like similarity measure. So it's something that really measures the similarity between two inputs. More mathematically, what this means is if 1 and 2 is true, then K xx prime will always have this form, which is that so computing the inner products after embedding x and x prime into some feature space. So that's why this one we impose 1 and 2. And in fact, if you think a little bit, if K is of this form that I mentioned to you, okay, if it's an inner product, then it has to be symmetric because this inner product is a symmetric. So that this second condition has to be true. And also this positive definiteness, the number 1, also have to be true because this inner products that we are using at the bottom, learn that. Yeah, so this inner product that we are using at the bottom is going to satisfy essentially satisfy the so-called linearity, bilinearity property. So if you use this number one property is also going to be true. Okay. So I just said if K is defined this way, and these two properties will be true. But the point is that if these two properties are true, then there is always a possible way to view K in this way. Okay. So that's what I'm going to explain a bit later. But before going there are a few important things that I want to mention to you, and which we're going to use. So the definitions of the kernel can also, for these two conditions, 1 and 2, especially the conditions about positive definiteness. So this positive definiteness for a fixed M, Ci, Cj, and Xi. I mean, for Xi and Xj. And then this symmetry can be expressed in terms of matrices, properties of the matrix. So then for fixed M, and then x1 up to xm. Number. So then 1 and 2, with respect to this specific m and x1 up to xm, it can be phrased by saying the following matrix. So we're going to write a matrix K, which is a m by m matrix, and defined by K ij is kernel K applied to xi and xj. We said that K is symmetric, which means that transposing K is going to be the same as K, and positive semi-definite. So this positive semi-definiteness, the space a bit larger. So, right. So this positive semi-definiteness means the following. It's about matrix. The positive definiteness that we define is about the kernel function. Positive semi-definiteness here we are talking about is about the matrix. They say that for any the vector C, which is m dimension, if we compute this quantity, transpose K, that is always greater than 0. That's what positive semi-definiteness. I mean, don't be confused. I mean, I myself got confused quite often. There are two terminologies which looks a bit inconsistent, but that's the life. The textbook said that's the official terminology. So we are using this greater than equal here, also the greater than equal here, which correspond to each other. But in one case, for matrix, we are using positive semi-definite. But for the kernels, we are using the positive definite. So they are related, but but then it turns out, according to the textbook, this is the official terminology. So that's a one property, which looks like almost the same as number 1 and 2. But here's just something more important. More important. So then perhaps you don't remember about this, but this is the second property, the symmetric and positive semi-definiteness implies the following. That is equivalent to saying, then K is symmetric, and case eigenvalues are real and non-negative. So you maybe some of you may forgot about what eigenvalues are. So the eigenvalues of a matrix. Okay. So eigenvalues of the matrix is the one, if we have some vector of a matrix, vector such that if you multiply it to k, if vector doesn't really change its direction, but just have a constant alpha, so then if such a vector v exists, we say vector v is an eigenvector. The alpha is an eigenvalue. So this means that the k is actually a transformation of a vector. And then this v is something that's kind of preserved by the k. Okay. So and then those are the eigenvectors. And then but there are some change. This alpha really measure the change. And then this symmetric ensures that, typically these eigenvalues may be complex numbers, but symmetry ensures that this alpha is real, that there are real eigenvalues, that all the eigenvalues are real. And then this positive semi-definiteness implies that all these eigenvalues are, this alpha are non-negative. Okay. But the important bit is, if this property is true, then we can do so-called Eigen Decomposition. Using some properly normal, the orthogonalized eigenvectors, which are these eigenvectors, as well as using these eigenvalues. If we put them appropriately, then we can achieve the following matrix. So this is the important bit that we're going to use later. So this matrix K can be decomposed, can be made into the products of three things. U is an orthonormal matrix. Transpose. So orthonormal means that U transpose U is going to be the identity matrix. And then the sigma is the matrix of the eigenvalues. So it's a diagonal matrix. Such that all of its diagonal entries, because eigenvalues are non-negative, all the diagonal entries will be greater than or equal to 0. So if you have a kernels, and if you build a matrix K here, and then that matrix K will have this decomposition. And we're gonna use this decomposition, to later to analyze some, to show that certain constructions on the kernels preserve produce a kernel. Also, we use this to construct, build another kind of kernel. Right. Just last bit is that this K actually has a name. I use colors with arbitrary way, but the kernel K has a name, and then the K is called ground matrix. Sometimes called kernel matrix. So of the kernel as with respect to the inputs x1 up to xn. So this is the name that appears often. Okay, so just to sum up, the kernel is this kernel. Okay. So this kernel is a functions from the two inputs to the real number, but we say the kernel, we only consider so-called PDS kernels, positive definite symmetric kernels, and those conditions are, so this condition that we see here for any Ci and Ci's and the Xi's, what you see at the bottom, in the screen is going to be greater than or equal to 0, and then it has to satisfy symmetry properties. And then I said these two conditions, later we will show that it's equivalent to saying this kernel K can be understood as computing the inner products after embedding each input into using the feature map to some space. And then the last bit is that these two conditions is equivalent to say the particular matrix that we'll construct here, which is a ground matrix or kernel matrix. It's going to be satisfy certain property, and particularly we are interested in this property that K, if we have a kernels, the matrix that we construct will have this decomposition. They decompose with U, sigma, and U transpose, right, where the sigma, diagonal matrix sigma, will have only non-negative entries. Right. So what are the example kernels? So the one example is we just working this one. Okay, so the first example is the polynomial. So if we have suppose our x is just r to the n, and then the fixed non-negative constant c and some degree natural number n. So then if let's define k, x and x prime, using first compute the inner products of x and x prime, then add c, and then the exponentiated, take the dth power of that term, and this is going to be a PDS kernel. And the inner product here is a PDS kernel. Because what the condition PDS really try to capture is that we are really computing the inner product. But for for K is defined this way. That also a PDS kernel. And I said that this positive definite symmetric property is really about saying we can view what we are computing here as an inner product. And we can see this in this case. If you take something simple, like, so if they say, consider d is equal to 2. So d is equal to 2, and n is equal to 2. So we have a point in the plane, and then we take the second power, and in that case, when we can view this k, x, and x prime as computing the inner products of the following map. Where V is a map from original 2-dimensional space into 6-dimensional space. Okay. How does V defined? V is defined as so let's just make it clear. So x has a so each x the two coordinate x1 and x2. So if we give x1, x2 to the same as x, so then the x6 is obtained by taking the x1 square, x2 square, square root of 2, x1, x2, square root of 2c, x1, 2c, x2, c. So if you use this P as a feature map, so you take a point in the plane and computing the quadratic terms, all the up to the constant linear terms. So it computes the constant linear terms, all the possible quadratic terms with the appropriate constant here and there. So then, if you take the inner products, that you can actually see that what we're gonna get is exactly the same as the polynomial kernels that we defined above. So this K, this is called polynomial kernel, and that is exactly in this specific case, that is exactly the same as the inner product that I shown here. So you can see that, we can prove this is satisfied this PDS property, and then that's also, you can also see that K in this case can be expressed as an inner product in 6-dimensional space. So one kind of main theme about the kernel method is that by using kernels, we are really using very expressive features implicitly. And then one way to understand what's really going on in the kernel is really to think about this feature space. And if you have some understanding about the feature space, that will help you to, they will help to use appropriate kernel for your problem. So what's the second example is actually something very, very popular for RBF. So I think it's a radial basis kernel. Or sometimes called Gaussian kernel. So this is called a polynomial kernel. So this is typically RBF or Gaussian kernel. And it's defined like this. If you have can assume that X is n-dimensional space, then K of X and X prime is defined by taking the exponentiations of 2 sigma square. It's a bit like a probability density of the Gaussian distribution. So we first subtract, take the distance between X and X prime. So by subtracting it, computing its size, we square it, and then we take the exponentiation. So if you can see that if X and X primes are very far away, the distance will become very large. So that means the K will have a very small value because it's an exponentiation of minus. But if X and X primes are the same, then the value is going to be 0. So then it's going to have the largest value, which will be 1. Okay. So, and this is something that's used often. And then I said later we will show that this is actually PDS kernel. Satisfy positive definiteness and symmetry properties. And then I said that implies we can view this K as the inner products. So in other words, using K, this RBF kernel, means that we are using some feature map. Okay. Then we may ask, okay, what kind of feature map we are using here? And Actually, the kind of feature, I mean, the intuitive informally, the phi of x, I mean, this is not a formal definition, but phi of x is really the polynomial of any degree. So if you have the R, say Rn, then we may have this constants, some constant. And then second term is each coordinate are x1 to xn. Maybe there may be some constant there. And then the quadratic term, x1 square, x2 square, and so on. And then cubic term, cube, x1, x2 cube, and square, and so on. So it amounts to using the feature which is created by taking polynomials of arbitrary degree, or monomial of arbitrary degree. So this term, the multiplication of variable and constant, they are called monomials. So it's a monomial of arbitrary degree. That's what is implicitly being used whenever we use the RBF kernels. And there is another property which is called normalizations. So these two are, in a sense, big characteristic of this RBF kernel, and understanding about them will really help you to see where RBF kernel may be useful. The third one, so is something called sigmoid kernel. Textbook said this is closely related to the neural network. But I think I have to solve the exercise in the textbook to see how this actually works. I mean, in this case, it's the same assumption, x is r to the n. And then the kernels k, x and x prime is defined by taking tanh of a xx prime plus b, where a and b are non-negative. And tanh is, is really I think the best way to show you tanh is like functions which goes from maps entire real line to the -1 and +1. So it goes like this and then moves like this. So the smallest value it has approaching is -1, largest value is approaching is +1. So this k xx prime is obtained by like this, and this also turned out to be a PDS kernel. And then I heard it's closely related to the behavior of the neural network. Okay, so these are the examples, and later we will see a lot more examples. But then I think let's move to the most important bit about the kernels. So I said the reason we impose these two conditions is that with these two conditions, the kernels can always be understood as an inner product on some implicitly defined the space, the implicitly defined feature space. And then the next things that we're going to show is that we will really identify the space. The space is called reproducing kernel Hilbert space. I mean, if you read machine learning papers, this RKHS will appear many, many times. Okay. So we were gonna prove some heavy theorem, and then that theorem say the following intuitively. So actually, I can state the theorem here. The theorem 6.8 in the textbook. So what the theorem say? The theorem says, if you suppose we have some input space x, Then suppose that we have a PDS kernel on X. So what's important here is that we are not thinking about arbitrary kernels. So we are thinking about this PDS kernel. So in that case, the theorem said there exists a Hilbert space H and a map V from X to Hilbert space such that the following conditions will be true. The first, this exactly expressed the kernels. So the kernel have the representation that I told you before. K of X and X prime will always can be expressed as taking the inner products of phi of X and phi of X prime over this Hilbert space. So for X and X prime. And then the second, so the first one really talk about the things that I just told you. The second, and the other properties are now telling us how this H and phi actually look like. Okay, given information about H and phi, and then the second say that this Hilbert space H, it consists of functions from X to the real number. Okay, it's not set of all the functions, but it consists of set of functions from X to the real number. The third, say this phi, it also say about how phi actually look like, phi of X. So then this has to be an element in H, which is another function. Then say that phi of X is actually applying this kernel K partially. So if you only apply kernel K with the first element, then it's going to be a function on the second element. So that is exactly this feature map. So partially applied kernel is going to correspond to phi of X. So that also implies this partially applied over X. That also implies, this partially applied K, they are all going to be in H. Okay. So then the fourth one is called a reproducing property. What this tells us is that for X and for H, then because H is a function, we can apply the function. But it turns out this is the same as taking the inner products of H and then the feature of the feature functions of X. Okay. And this because of the 3, this is the same as H and the partially applied function K. So that's the third property, and this is called reproducing property. Okay. So this is actually quite important theorem. By the way, I think some of you have no idea what Hilbert space is. So the Hilbert space is a bit like R to the n, but more generalized. So this. So some maybe wonder what Hilbert spaces are. Yeah. So they are vector space, which means that we have addition and constant multiplication. And we also have an inner products in vector space plus we have an inner product operation. So if you have this much, this is called inner product space. And Hilbert space means we have one more, we have enough limits. So that means all the so-called Cauchy sequence, which are something becomes closer and closer, I mean, they all have a limit. So this is called completeness. So having these four properties is called, they are the one that characterize the Hilbert space. Vector space plus and constant multiplication plus inner products, which is a binary operation, which are all linear in each argument and satisfy so-called positive semi-definiteness. But it really, if you don't know what it is, then it is something behave very much like inner products that you are familiar with. And the limits of all if it satisfies these three properties, that's called the Hilbert space. So there's a very nice space where we can talk about limits, the inner products, and sum of two elements, and the constant multiplication, and some map that maps every inputs into this space H, which have this rich structure. Okay. And later, if you are more questions instead of the analysis, when we were really looking for some structure, I mean, the particular H and P that we're gonna construct and what this theorem claim to exist is a so-called universal. I mean, I'm gonna tell you about this later. So this is something that's, in a sense, can be constructed without using any extra information other than all the information available in K. Okay, and then this H has a name with H and P that's claimed to exist by theorem 6.8. It has a name that's called reproduce RKH, as reproducing Kernel Hilbert space of K. Okay. So now the question becomes how to construct such H. Okay. Okay, we have about 15 minutes. So how to build H? And then we're gonna build H in 2 steps. So we'll first build H0. But this H0 is not quite Hilbert. It satisfies all the good properties there, except that it is just inner product space. Not necessarily Hilbert space. In other words, it may behave bad, it may miss some of the limits. Okay. May not include some limits of so-called Cauchy sequences. And then build H from H0 by so-called completion. So this intuitively what this completion does is, I mean, I said this H0, I mean, we want to construct Hilbert space. Hilbert space has to be, I mean, so Hilbert space has to be the vector space. So it has to be a vector space with the inner products and limits. And what I'm saying about H0 is that it has almost everything except that it may miss the limits. So then the way to construct H is essentially by adding all those missing limits. So but there's a systematic way of doing this called completions. Mathematically, you just construct a space with Cauchy sequence and quotient this. So there is some systematic way of doing this. So then we're gonna apply the systematic construction to H. And that will preserve all the nice property of H0. So that's why we can complete the construction. So in the proof, we only focus on the construction of this H0 part because the completion is quite involved in math, but and also it's quite canonical. Okay. So we'll on H0. So now the question is how to build H0, and here's our way of building this. So we will build H0 to be super span of a function which is constructed by partially applying the k to some input, okay, where x is coming from x. So what does this really means is that we're gonna consider, so span means all the linear combinations of finitely many terms. So this means our set H0 will consist of these things. Some m, the ai, k, xi, ai is some real numbers, and then xi is an element of x. And then the m is some natural number. So if you do so, so this is how we will construct this will mean construct set of functions. So if you do so, so then multiple things, multiple requirements can be checked. Okay, so that's, so then first H0 is a vector space. In other words, we can define additions and constant multiplication. I mean, because our terms here, they are all defined by sum. If you have adding these two things, we just need to increase the range of this summation. So H0 is closed under sum of two functions of this form. This form that we have here. And then also for constant multiplication, we just need to change this AI by with this constant. So this is also closed with respect to constant multiplication. So it's a vector space. And furthermore, it is also have this H0 is a subset of, every element is a function from x to the real number. So we can tick this number 2, and then the vector space part is we also tick it. I think it's maybe not visible. We can tick this and tick this. Then now we have we've moved to this third. For the third, we just define for phi of x, we define it as a partially applied function. So then that is in H0, I mean, by our definition of H0. So this third part is also ticked. And then we said we are not really worried about the limits. So this is something that we don't have to worry about. And what it remains is we have to first show, the number 1. We have to first show that not first, we have to show, find the right color. We have to show the inner products. So, and then this number 1 and number 4, they are the ones that we have to prove. Now, how to define the inner products? So what remains? So how to define the inner product? Here's a definition of our inner product. So I'm gonna cram lots of things here because I don't have much space. So how to define the inner products? So inner products, two terms, I 1 through m, ai, k, xi, and j 1 through n, bj, k, yj. The inner product is defined this way. I j is equal to 1 through m, ai, j, k, xi, and yj. So if we define like this, then it's, I mean, we have to still show, we have to prove this. Something that's defined this way is really inner products. And then, I mean, the first, before actually talking about this, these things we have to show is well-defined. So that means if we have the first inputs, we may have two, the input of this form, but may have a different representation of the same functions by I is equal to 1 through m prime, so ai prime, k, xi prime. So representations and what the formulas are different, but the function they are defined may be the same. So we have to show this definition doesn't really depending on the representation. So that's a well-defined in this question. And both of them can be proved quite easily, okay? And just by calculation, we can prove this. So I'm gonna upload my lecture notes likely early next week. But then if you see the lecture note, you will see that the formal proof about both of these properties. And to show the formal proof about this well-definedness, for the inner product, we have to show that this operator is bilinear. And this is also quite easy. And then we also have to show so-called here again, the word positive semi-definiteness appears. Let me not mention this, and then and there's one more property, which is something that we're gonna focus on. So there's this extra property, and what is that extra property? The property say, if you have a H, take the inner product, that's always greater than equal to 0. And if you H and H is 0, that implies function H is itself is 0, which means the constant 0 function. So any input, it always returns 0. So this is something that we have to prove. And for the first, if you have an H, so now suppose this H have this form, summation of AI, K, xi, rank, I is equal to 1 through n. So then this so if you express it like this, so then this inner products becomes whole inner products becomes summation of ij, which is from 1 to m. So ai, aj, k of xi and xj. And you can notice that this is exactly with a positive definiteness property of k. So that's always greater than or equal to 0 because of positive definiteness. Okay. So the first is true. Now the second is more challenging. Okay. I think I will overrun maybe 3 minutes today. This second part is more challenging. For the second part, we note the following. Okay. So suppose this HH is equal to 0. So then now pick any x. Then we can compute this h of x. This is sum of I equal to 1 through m, ai, k, xi, x. But that is the same as taking this inner products. And k, this h, and then the k of x comma blank. So because that's the definition of the inner product. But it turns out, so now if you square them, all of this, let's square. But it turns out, if we have something that looks very much like inner product operator, so well-defined bilinear operator which satisfies this positive semi-definiteness, which is this property, then there is a so-called Cauchy-Schwarz inequality is true. So this is smaller than equal to HH times K of X blank, K of X blank. So this is the standard Cauchy-Schwarz inequality, but this is true. But the first part is equal to 0 by our assumption, so the entire thing has to be 0. So that means H of X also have to be 0. So that's how you can prove that that's the second. Okay, so where we are, so we just showed that with our definitions, so we have a well-defined notion of the inner products. So this is something that we are done. Now it remains to show this number 1 and 4, and that's actually quite easy. So let me show you the number 1. So give me 2 more minutes, then I will finish. So then what number 1 say is the Conor is really computing the inner products after the mapping inputs to the feature via feature map. So we have a k of, see really the case, that's what we have to check. K of x comma x, by the definition of inner product that we define, that is same as x comma blank, k of x prime comma blank, and that is really p of x and p of x prime. So that's 1 is done. And the number 4 is a reproducing property. So then this reproducing property say for any h and any x. What this exact mean? This should be expressed in terms of inner product. But then if we have an h, then h will be of this form. It's 1 to m, ai, k, xi blank. So this will, if this h of x is going to be same as sum of I is 1 through m, ai, k, x of I, x. But now by the definition of the inner product, this is the same as m ai kxi k x blank. That is exactly h feature map f p of x. So that concludes the first property. So that we are done here. Okay, so just to sum up, what we just proved these two, and although we didn't quite show the completion, that give a kind of idea about how the entire proof will work out. In the textbook, there's just something not quite right. I mean, you have to use a Cauchy-Schwarz inequality in a way that I just explained. The way the textbook explains, I think it's not quite right. So anyhow, the theorem 6.8 said if we have a PDS kernel, there is a very canonical Hilbert space whose elements are functions, feature map, which is defined in terms of partially applying the functions in such a way that this kernel can be expressed. So the kernel can be expressed in terms of the inner products after the application of the feature map, and then that Hilbert space have a nice property which is called the reproducing property. Okay, so I will mention a little bit about this more than the next time, and then we will move on the construction of various kernels. Okay, so thank you very much, and sorry for overrunning it.